Okay, hello, welcome. I'm going to be talking to you for about an hour about number theory, which is something I'm really interested in, and I hope some of you will be interested in it by the time we're finished as well, and some of you may not be, and that's fine. My face will disappear in a minute because I'm going to have to write some stuff down, so you won't be able to actually see me, but you'll be able to hear me. So maybe I'll just give a brief introduction of myself. I'm Will. I'm a second year. I've just finished my second year studying maths at Oxford. Number theory is something I'm really interested in. It's what I'm going to continue to do next year. It has lots of very important applications to computer science and in particular cryptography. I don't think we'll get quite as far as explaining the details of that, but you can know that it is very important in computer science, and then kind of the other way around, computer science is very important in number theory. Some of the most important unsolved problems in maths at the moment, such as the Riemann hypothesis and the twin prime conjecture, have lots of computer science methods have helped to provide some evidence for whether these unsolved problems are true or not, because we can check on a computer lots of different aspects of these problems. Number theory is very exciting. Like I said, lots of kind of the biggest unsolved problems in maths are about number theory, which is why I'm quite drawn to it, I think. I think the other beauty of number theory is lots of these unsolved problems are relatively easy to understand. So an example is the twin prime conjecture. You can look this up on the internet, and I think you could watch a kind of 5-minute video on it and you'd understand what the twin prime conjecture says, which is not the case in the rest of mathematics, but is still very much unsolved, which is kind of a very interesting balance. So we've only got an hour, and let's get started. I'm going to disappear now. Okay, let's get started. So, like I said, I'm going to be giving you a bit of an introduction to number theory. So maybe I'll tell you first what number theory is. This seems like a good place to start. So number theory is the study of whole numbers, integers. It's kind of the mathematical term for what they're called. So these are the numbers 1, 2, 3, ... And then you can also have 0 and the negative numbers as well. So we're interested in the properties of these numbers. And I mean, at the very basic level, this doesn't seem very difficult, right? When you're in school, from the age of 5, you learn about whole numbers, or even younger than that. You first learn to count, then you learn how to add numbers together and then multiply them. And that kind of seems like it for quite a while. And then I think the closest you get to number theory in the rest of your mathematical career at school is learning about things like highest common factors and prime factorizations and lowest common multiples and things like this. But other than that, you study very little number theory at school. I'll maybe tell you how much you would study at university. So in the first year, you learn a little bit about number theory in a couple of courses called groups and group actions, and then constructive maths. So these two courses in the first year at Oxford would give you a bit of an idea about what number theory is about. And then in the second year, there is a course on number theory. And in the third year, there is a course called algebraic number theory. And kind of from then on, in the fourth year, there are lots of different courses you can take that are very heavily related to number theory. So this shows that this really is quite an important topic, and there is a lot to learn. There are lots of the fact that there are lots of fourth year maths courses at Oxford about number theory shows that it is quite a difficult topic. And I think I'll try and give you an explanation as to why it's so hard. So imagine if you were creating maths from scratch and you could kind of pick the rules about how everything works. I think, for example, if I asked you to pick a rule of what 2 plus 3 to the power of 5 is, it would be quite nice if it weren't like this, right? If it went 2 to the power of 5 plus 3 to the power of 5. But this isn't how it works. Addition and multiplication, or addition and powers, kind of same thing, don't work in a very nice way together. And I think this really is at the heart of why number theory is such a difficult thing to study. Whole numbers are very interconnected with addition, and then when you try to ask questions about multiplication and powers of whole numbers, things get very complicated very quickly. So maybe to demonstrate this to you, I'll tell you a little bit of history. So in 1997, Andrew Wiles. So Andrew Wiles, you can look him up on the internet. He's a mathematician at Oxford, actually, and the Maths Institute at Oxford, the kind of building, is called the Andrew Wiles Building. So he's a very successful mathematician. He solved a problem called Fermat's last theorem. And this was something that was proposed by a mathematician in, I think, the 17th century called Pierre de Fermat, a French mathematician. And for 350 years or something, this was an unsolved problem. No one could work out how to prove that it was true or false. So that tells you something, that it took 350 years. And then finally in 1997, Andrew Wiles solved it. So I'll tell you what the problem actually was. So what does Fermat's last theorem say? It says there are no whole number solutions to the equation a to the n plus bcn equals ccn for n bigger than 2. So maybe this looks a bit complicated in this form, but if we think about first what happens when n is 2, this is the equation a squared plus b squared equals c squared, right? Which is quite familiar. This is kind of Pythagoras' theorem for right-angled triangles. And we can think of whole numbers that satisfy this. For example, 3 squared is 9, 4 squared is 16, and if you add them together, you get 25, which is 5 squared, or maybe a different one is 5 squared is 25, 12 squared is 144, and if you add them together, you get 169, which is 13 squared. And you can find infinitely many triples like this for squared. But what Fermat's last theorem says is if I increase this by 1 to start with, you can look all day and you will never find whole numbers that work here. And then similarly, if I increase it again, you will never find whole numbers that work here. And if you increase it again and again and again, you will never find any solutions above a power of 2. So this is a very powerful statement, but it's really, really hard to prove. The proof, which is kind of a formal mathematical document explaining why this is true, is hundreds of pages long. It took Andrew Wiles years and years of his life to work out why this was true, and many mathematicians had tried and failed to do this. But it's a problem that I can explain to you as A-level students, right? This isn't that difficult, relatively speaking, to understand what it's saying. I think this shows you, one, how difficult number theory is as a topic when you get to the advanced level, and two, how kind of beautiful it is, as in the problems are very easy to understand, but then solving them is sometimes incredibly difficult. Okay, so that's a bit of historical context about what number theory is about. Let's get on with actually doing some. So the first thing I'm going to do is tell you what modular arithmetic is. And lots of number theory problems rely heavily on modular arithmetic. So modular arithmetic you actually kind of see in your day-to-day life relatively often, in the form of the time. So if I tell you the time is, I don't know, 7 a.m., what will the time be in 8 hours? Is the question. Well, maybe you do 7 plus 8 and get 15. And when we see 15, we wouldn't say it's going to be 15 o'clock, right? You'd say it's going to be 3 o'clock. And you get to the number 3 because 15 is 3 more than 12, right? This is 12 plus 3. And this is an example of modular arithmetic. Saying that 15 is 3 more than a multiple of 12 is the same as saying that 15 is congruent, or we can just say the same as 3 mod 12. Okay. So I'll give you some more examples of this to kind of solidify your understanding of some numbers. So maybe 6 is the same as 11 mod 5, right? Because 6 is 1 more than a multiple of 5, and 11 is 1 more than a multiple of 5. Maybe a different example is 6 is the same as 1 mod 5, right? Because 6 is 1 more than a multiple of 5, and 1 is 1 more than a multiple of 5, where the multiple of 5 we're talking about there is 0. Kind of, we think of 0 as 0 times 5, so it is a multiple of 5. Maybe 9 is the same as 2 mod 7. Right, because 9 is 7 plus 2, and 2 is 0 plus 2. But this is also the same as 16, right, because 16 is 14 plus 2, and it's the same as 23, because 23 is 21 plus 2. Okay, so I'll write down a more formal definition, and it might not be clear at the moment why my definition makes sense, but hopefully I'll be able to convince you that it does. We say that A is congruent to B mod n, which means A and B are the same mod n. So kind of in our examples above, 6 and 11 mod 5, 6 and 1 mod 5, 23, 16, 9 and 2 mod 7. These are all the same. You say that A is congruent to B mod n if a minus b is a multiple of n. Okay, so now let's return. Okay, so now let's return to our example above and check that this definition kind of makes sense and is consistent with what we thought modular arithmetic was earlier. So 6 minus 11 is minus 5, right? And that is a multiple of 5. So this kind of seems to fit our definition. 6 minus 1 is 5, which is a multiple of 5. Again, this fits our definition. And then kind of if we pick any of these pairs here, I don't know, 23 minus 9 is 14, which is a multiple of 7. And I'll pick one more, maybe 16 minus 2, again is 14, which is a multiple of 7. So these are kind of the same thing. So there are two ways of thinking about modular arithmetic. Just to recap, two numbers are the same, say, like here, 6 and 11 are the same mod 5 because they're both one more than a multiple of 5. 6 is one more than 5, 11 is one more than 10. But equivalently, two numbers are the same mod 5 if their difference, so 6 minus 11 in this case, is a multiple of 5. So these are the same definitions. So don't worry if you don't have a complete understanding of what this means. But if you get the kind of basic idea of what we're talking about, that will be enough. So modular arithmetic is very important in number theory because it allows us to describe relationships between whole numbers in a very succinct way, right? In a way that is very easy to write down. It was first, just for some context, it was first kind of developed in this format by Gauss, who was a mathematician in the early 19th century, I think. He kind of presented it in a textbook in about 1800. And it kind of crops up all over maths, but is particularly important in number theory. So, as for the outlook for the rest of what I'm going to talk about, my aim is to try and prove something to you, which I think is a really neat result, which is called, I'll write it down here, Fermat's Little Theorem. So this name might ring a bell because we were just talking about Fermat's last theorem. I'm not going to prove that to you. I wouldn't be able to. And even if I could, it'd take me hours because that's the really difficult problem we were talking about before. This is a different kind of result by the same person, Pierre de Fermat, who was, like I said, a mathematician in the 17th century. And this is about powers and prime numbers. So I haven't mentioned prime numbers yet, but these crop up all over number theory. So let me write down what it says. So I'm going to say let P be a prime number. So just kind of to recap, a prime number is a number that's only divisible by 1 and itself. And 1 is not a prime number. And this is an important rule. Let A be a different integer. That isn't a multiple of P. So, example, if P is 7, we could have A is 1 is fine, 2, 3, 4, 5, 6. We can't have 7. We can have 8, 9, 12, 13. We're not allowed 14 because that's a multiple of 7, right? But we can have 15, etc. Kind of when we carry on like that. All of these values of A work. You're just not allowed to be a multiple of p. I'll get rid of that. And then what it says is then a to the power of p minus 1 is congruent to 1 mod p. So let's think about what this says in the two different definitions of modular arithmetic we gave. So one, maybe we could think of it like this. A to the power of p minus 1 is 1 more than a multiple of p. And then a different way of thinking about it is a to the power of p minus 1 minus 1 is a multiple of p. So remember, these were kind of the two different definitions we gave of what this congruence or modular arithmetic means. And I think this is neat for a couple of reasons. Firstly, because prime numbers are weird, and it seems strange that this only works for prime numbers. It isn't clear why the fact that p is prime is important, and hopefully that'll become a bit more clear later on. And I think also because it's just a bit it's not something you'd expect to be true. So maybe let's give an example of how this just instantly tells you something really unobvious. So maybe if we take p is 7 and a is 3, then we know 3 to the power of 7 minus 1, which is 6, minus 1 is a multiple of 7. Right, and you can check that. Maybe I'll do it. I've got a calculator in front of me. So 3 to the power of 6 is 729. So this is 729 minus 1, which is 728, which is like 7 times 104, right? So it just kind of like, it really doesn't seem at first glance obvious why this should be true. And it isn't at all. But my aim for the next kind of half hour or so is to convince you that it is true. So let's get started with that. Okay, let's have a go at explaining why this is true. First, I'll say that it doesn't matter if you don't completely get every step of this. That is to be expected, and it's partly just the nature of maths. As maths gets more difficult, it takes you kind of longer to understand more difficult concepts, and maybe it take you 2 or 3 or 4 or 5 times looking over an argument to really understand why it's true. And also, I might have to be a little bit kind of hand wavy at times and just tell you something is true without properly explaining why. So let's give it a go though. I think you'll be able to follow most of the argument. So proof. We're going to start by letting p be a prime number. Okay, this seems like a nice place to start. And we're also going to let a be an integer that isn't a multiple of p. Okay, so we're going to consider these numbers. Consider this list. So the first number on our list is going to be a. The second number on our list is going to be 2 times a. Then we're going to have 3 times a, 4 times a, dot, dot, dot. And then the last number on our list is going to be p minus 1 times a. So maybe I'll kind of do this as I go along the proof. I'll do this with the example we gave above. So where p is 7 and a is 3. So the numbers on our list would be 3, 6, 9, 12. And we're going to go up to, because p is 7, 7 minus 1 is 6, so we're going to go up to 18. Maybe I'll just write out the whole list. It's not a very long list, right? So these are the numbers kind of corresponding to the example above, and I'll do that in a different colour. So then what I'm going to do is times all these numbers together. So we multiply them together. So a times 2a times 3a times dot 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 times b minus 1a. We can rearrange this a bit. So maybe we'll have 1 times 2 times 3 times. So take all the numbers at the front first, and then we're going to have lots of a times times dot 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 times a. Right, so I've taken all the a's to the end, all the numbers in front of the a's to the front. So this number here, you may or may not have seen this at school, but we have a name for this where these are all the numbers up to p minus 1 times together. Right, so it's 1 times 2 times 3 times 4 times up to p minus 1. And we call that p minus 1 factorial and write it with an exclamation mark. And then the second part of this, we've got a times a times a times a. Well, how many a's do we have? Well, maybe it'd be quite useful to look here. We've got 1, 2, 3, 4, 5, 6 here, right? And similarly, up here we've got 1, 2, 3, 4, dot dot dot. There's p minus 1 of them, right? When you times a together, p minus 1 times, you get a to the power of p minus 1. Okay, so now I'll do this with our actual numbers. So we've got 3 times 6 times 9 times 12 times 15 times 18. This is 1 times 2 times 3 times 4 times 5 times 6 on one hand, times y, and then we've got all the 3s. 3 times 3 times 3 times 3 times 3 times 3, which is 6 factorial, is what we call that, times y, 3 to the power of 6. Okay. Hopefully that makes sense. So then maybe here comes the hand wavy bit. So we know that so I think the best way to explain this is the numbers 1, 2, 3, 4. So the numbers 1, 2, 3, p minus 1 are all the numbers mod p. As in, every number in existence that isn't a multiple of p has to be congruent to one of these numbers. Okay, so I'll say that again. Every whole number, has to be congruent to one of these numbers, mod p. Well, why is that? Because every number is either a multiple of p or 1, 2, 1 or 2 or p minus 1 more than a multiple of p. So let's take some examples in a different colour. So if p is 7, so for example, 64 is 63, which is 9 times 7 plus 1. Right, so it's 1 more than a multiple of 7. 107, this is going to test my mental maths. This is, I think, so 105 is a multiple of 7, right? Because that's 15 times 7 plus 2. So that's 2 more than a multiple of 7. Maybe 216 is 210 plus 6, right? And this number on the end, we can always make sure that this is less than 7, right? Because if it's not less than 7, then say we wrote this as, instead of 63 plus 1, we could write it as 54 plus, 56 plus 8, right? But then this is like 56 plus 7 plus 1. So we can split that 8 up to write that as 63 plus 1. Right, we can always reduce this number to something that's either 1 or 2 or 3 or 4 or 5 or 6. Right? So, back to what we said, the numbers 1, 2, 3, ... p minus 1 are all the numbers mod p, if we're not including multiples of p. Okay, so then what can we say? This thing on the left-hand side is a times 2a times 3a times ... times p minus 1a. Because 1, 2, 3, and p minus 1 are all the multiples, all the numbers mod p, then, and this is where the fact that p is prime comes into play, and this is the bit that I think maybe you're just going to have to believe me on, because this isn't completely obvious. If we times by a, we still have all the numbers mod p. They all are still there, right? So a, 2a, 3a, ... and p minus 1a are also all the numbers mod p in some order. Okay, and this is just a fact that you kind of have to believe me on. So what that means is these two lists of numbers, maybe they're in a different order, but they're the same lists, right? This list here and this list, they are the same list in some order. So what that means again is if we times them all together, if we times all the elements in one list together, and we times all the elements in the other list together, we're going to get the same thing, right? Because they're the same list. So kind of numerical example, if we have these two lists, 2, 3, 7, 3, 7, 2, if we times all the elements in here together, we get 2 times 3 times 7. And if we times them all in here together, we get 3 times 7 times 2. And these are the same thing, right? So this is what we're going to do. So what this is telling us is 1 times 2 times 3 times ... times p minus 1 is going to be the same as a times 2a times 3a times ... times p minus 1a mod p. But let's think about what both these sides are. So the left-hand side is just our definition of p minus 1 factorial. Whether you've seen that or not, that's just, we can just call it p minus 1 factorial. It doesn't matter too much. And then the left-hand side is what we worked out earlier, right? It's up here. P minus 1 factorial times a to the p minus 1. So we've got p minus 1 factorial times a to the p minus 1. These are the same. And then what we can do is kind of like cancellation, right? We can divide both sides by p minus 1 factorial, kind of. So we get 1 is congruent to a to p minus 1 mod p, which is exactly what we're trying to prove. Okay, so I think the most difficult bit here, let's just look over this. I think the most difficult bit is where we say, where we kind of times by a and said that those lists were the same. So let's see this with an example with p is 7 and a is 3. So with p is 7, we want to show the lists 1, 2, p minus 1. We want to show that this is the same as the list A, 2A, 3A, p minus 1A, mod p. So let's just write out the first list. So if p is 7, so the first list is 1, 2, 3, 4, 5, 6. Right, that's kind of the easier list to deal with. Now let's write out the second list. The second list is 3, 2 times 3, which is 6, 3 times 3, which is 9, 4 times 3, which is 12, 5 times 3, which is 15, 6 times 3, which is 18. Right, but so these don't at the moment look like the same list, but remember we're kind of in mod p world, so mod 7 world. So we can change all these numbers. Well, 9 is the same as 2 mod 7, for example, because 9 minus 2 is a multiple of 7. 9 is 2 more than a multiple of 7, that's a different way of saying it. 12 is 5, right? 15 is 1. And 18 is 4. So actually, this list becomes 3, 6, 2, 5, 1, 4, which is the same as this list, just in a different order. Okay. So this relies on the fact that p is prime. This doesn't work in general if p isn't prime, which is kind of the difficult bit of the proof. Okay, but I think the majority of this, if you've kind of followed the general argument, you've done well, I think. It's not easy, but difficult result. If you want an important or difficult result in maths, the proof is normally going to be a bit hard. So let's see, we saw an example of this earlier numerically. Let's see another one. So maybe let's do one on a slightly bigger scale. So let's pick a big prime. So maybe p is, I don't know, 83. I think that's prime. Feels like a prime number. Yeah, that's prime. So, and then we'll pick a, could be anything that isn't a multiple of 83. So maybe we'll pick I won't pick it too big actually. Let's pick 11. Then Fermat's little theorem tells us that 11 to the power of 83 minus 1, which is 82, is congruent to 1 mod 83. So 11 to the power of 82 minus 1 is a multiple of 83. And this is not obvious at all, right? Like I said earlier, this really gives some non-obvious results. If I asked you at the start of this talk, is 11 to the power of 82 minus 1 a multiple of 83, you'd have no idea, right? And I think that's the beauty of this result. Okay, so that finishes the proof, and now we're going to talk about some actual computer science and algorithmic applications of this. Okay, so I've got about 20 minutes left, and I didn't think I would get around to talking about cryptography, but I think we have time. And it's not easy, but it's very interesting. So let's give it a go. So I'm going to try to explain to you how public key, private key, cryptography works. So what this means, this is the way that your computer or your phone transmits information securely from one place to another. So this is exceptionally important because, I don't know, if you want to buy something online, for example, you trust when you put your bank details in that some random person can't kind of, as the bank details are flying through the sky from you to the person you're buying something from, you trust that no one can kind of intercept that message and get your bank details. And if they could, that'd be a big problem, right? So the first thing to know is this relies on a very important fact. So, fact. It is easy, whatever this means. So this means it means a computer can do it in a reasonable time to multiply two prime numbers. Together. And this is easy even if they're really, really big prime numbers. And generally in this application, they are really big prime numbers, hundreds of digits. It doesn't take long to times them together. But it is hard, whatever that means, to factorize the product of two prime numbers. So, for example, if I give you a massive number, 1047, right? So this is a big number. And if you told your computer to find the prime factorization of this, it would take it a lot long. It would take quite a long time to do it, relatively speaking. And once you get really big numbers with hundreds of digits, it effectively can't do it. It just can't do it in any reasonable time. So this is a fact. You just kind of have to believe. It's actually, for those of you who are interested, it's not a fact. It's assumed to be a fact. But it's a very strong assumption. So this is an application of something called the P versus NP problem in computer science. So almost certainly this is a fact, but no one has actually managed to prove it yet, that there's no easy way of factorizing prime numbers. Okay, so this is a fact. We're also going to rely on something else. So Fermat's Lispel theorem said that a to the power of p minus 1 is congruent to 1 mod p. I'm going to generalize this a bit and say a to the phi of n is congruent to 1 mod n. Okay, so phi of n, if n is prime, so phi of n is p minus 1, right? This just kind of, is n minus 1. This translates into what we had before, right? If n is not prime, you just kind of have to believe me, we can find this number. There is a number that this always works for. So this is something called the Fermat-Euler theorem. Okay, so this is just an assumption we have to make, and that's fine. The details aren't very important. It's a very similar thing to Fermat's Lispel theorem, just a slight generalization of it. So we're going to have two people, as is kind of common in explaining this, Bob and Alice. And Alice wants to send a message to Bob. To send a message to Bob. And then there's an eavesdropper. Eve hears everything. Okay, but we don't want Eve to know the message. So this is what happens. Step 1. So Bob, the receiver of the message, so Bob is going to receive the message. Bob chooses two massive primes, P and Q. Okay, so these are two really big prime numbers. They probably have hundreds of digits each. Bob also finds a prime number E, this can be a lot smaller. So this could be kind of 7 or 5 or something. Bob works out N, which is P times Q. So Bob works out the product P times Q. And remember, we are assuming that this is easy. So this is what, if you're trying to send some details to a bank, the bank will do this. The bank will pick 2 massive prime numbers, times them together, call that number N. Bob publishes N and E. So everyone hears the number N and the number E. The key thing here is it's very difficult, as we assumed before, to find out what P and Q are from this, right? If you just hear N, because it's very hard to factorize big numbers, you won't be able to work out P and Q. And this is what this cryptography relies on. So now we go on to step 2. And this is what Alice does. So Alice, well, first we want to turn everything into a number. So makes the message a number. So there's kind of lots of different ways you could do this. Maybe you could take the letter A to 0, 1, the letter B to 0, 2, letter C to 0, 3, etc. So the message, an easy message is ABBA, would correspond to the number 0, 1, 0, 2, 0, 2, 0, 1. Right, if that's the message you wanted to send, you would take this number. Okay, and we'll call the number M. So in this case, it's 0, 2. So M is the message in general. Alice works out M to the power of E. We're going to do this mod N. Remember, she knows N, and she works out M to the power of E. So she's done her message to the power of E, this kind of relatively small prime number. And then she can work it out modulo N. It doesn't, all this means is she can kind of make it a number that is less than N. And then this number is published. So that's step 2. So if we just look over it again, everyone heard N, everyone heard E, and everyone knows M to the power of E mod N. But the only person who knows P and Q is Bob still. Alice doesn't know P and Q, and Eve definitely doesn't know P and Q, but Bob does, which is important. So Alice has sent the message. So step 3, Bob needs to work out what the message actually is, right? Well, the key thing here is that Bob knows P and Q, so can work out this magic number we were talking about earlier, phi of N. You don't really need to know how he works this out, but you can just trust me, he can. And it turns out that phi of N is P minus 1 times Q minus 1. This isn't particularly important though. No one else can work out phi of N though, because no one else knows P and Q. This is a really important fact. He then finds a number D such that D times E is congruent to 1 mod phi of N. or kind of another way of writing this is i.e. d times e is some number times 5n plus 1. So d times e is 1 more than a multiple of 5n. This all looks a bit complicated, but hopefully this makes it clear why he would want to do this. Remember, he knows m to the power of e. So then what can he do? Well, m to the power of e to the power of d, using our power rules, this is m to the power of e times d, or d times e, right? But this is m to the power of k times 5n plus 1, by assumption, right? By our power rules, this is m to the k times 5n times by m, right? Again, by the power rules, this is m to the 5n to the k times m. But the Fermat-Euler theorem, which I briefly mentioned earlier, tells us that this thing is congruent to 1 mod n, right? So this whole thing is congruent to 1 times by m mod n, i.e. it's congruent to m mod n. So what this tells us, what this kind of slightly tricky bit of algebra tells us, is that Bob can work out what n is. And this is exactly what Bob wants to know, right? Bob wants to know the message. And throughout all of this, the two things that allowed this to work was that Bob knows P and Q and no one else does. And kind of leading on from that, it is not easy to factorize the number n. If you know n, you cannot work out P and Q. And this seems like quite a basic fact, but if this wasn't true, the world would collapse, because no one would be able to send secure messages anymore. If someone worked out a really easy way of factorizing big numbers, every kind of online transaction would no longer be secure. People could just go on and work out your bank details for free. So it's amazing how important this fact is, just kind of in the real world. Okay, so I know that's probably quite a lot to take in. So let's do an actual numerical example and try and decode a message just quickly. So first, remember what Bob has to do. Bob needs to do a couple of things. So first, Bob chooses a couple of primes. So Bob picks, and in reality, the primes would be a lot bigger than this, but that doesn't really matter for the example. It wouldn't be helpful for me to pick primes that were 100 digits long. So Bob is going to pick P is 67 and Q is 43. So still relatively big primes. Bob also picks E, which is a small prime number. He's going to choose 5. Bob publishes E, which is 5, and N, which is the product of the primes, so 67 times 43, which turns out to be 2,881. So at this point, everyone knows N equals 2881, E equals 5. Okay, so Alice turns her message into a number. So we're not going to know what this message is because we're working from Bob's perspective. And she's going to split it up into 3 different parts. So it's going to be a 6-letter word, and she's going to split it into kind of 3 2-letter words, just because then the numbers are a bit easier. So that number's called M, right? But kind of in this example, it's going to be 3 numbers M1, M2, and M3. She calculates M1 to the E, M2 to the E, and M3 to the E. Right, because she knows E, and of course she knows what her messages are, so she can calculate these. And this is all modulo N. And then she publishes these messages. So Bob hears these messages. Now, this is kind of where the weird bit happened in the explanation of how this works. So Bob needs to find this number D, right? So Bob finds a number D in the following way. So step one, he works out 5n. And remember I said it was p minus 1 times q minus 1, so it's going to be 67 minus 1 times by 43 minus 1, which turns out to be 2,772. And then he finds D such that D times E is congruent to 1 mod 5n, 2772. Well, we can just check that this number works. D equals 1109 works. Because then D times E is 5 times 1109, which is what? 5545, which is 5544 plus 1, which is 2 times 2772 plus 1. So D times E is 1 more than a multiple of 2772. So D times E is congruent to 1 mod 2772. And then what we showed earlier was that M to the E to the D is congruent to M mod N. Okay, that was what was explained earlier, right? So now we can actually do some calculations. So Alice publishes. We know that M1 to the E is going to be, she published that it was 2352. M2 to the E is 2138. And M3 to the E is 0828. So then we can calculate M1 to the E to the D is 2352 to the D, which is 2352 to the power of 1109, which is, of course, a massive, massive number. But a computer will be able to tell you that relatively easily that this is the same as 1524 modulo N, which is 2881. Similarly, M2 to the E to the D is congruent to 0615 mod 2881. M3 to the E to the D is congruent in the same way to 1804 mod 2881. Right? But remember, because of this fact up here, we know that this must be M1, this must be M2, this must be M3. Well, so if M1 is 1524, well, the 15th letter in the alphabet is O, and the 24th letter is X. M2 is 0615. FO, and maybe you can see where this is going, RD. So the message Oxford. So hopefully that makes it a bit clearer. The only thing that is still a bit of a mystery, well, the two things are how we work out 5n, you just have to believe me with that, and how we found that value of d. We can check that it works, but actually finding it is slightly more difficult. But this is the overall method of how public key, private key cryptography works. So hopefully you enjoyed this, and the example was slightly more instructive than the complete explanation. I think this was probably quite difficult, but hopefully you found it interesting and gained at least something from it. And good luck with the rest of the summer school.